Okay, good morning. Welcome back. This is the second lecture in our course, Mass 2, Mass 802, Algebraic Topology. So, yesterday we look at we are trying to define some basic notions in topology. We define what we call a topology and topological space. And we also talk about the notion of closed sets in topological spaces. We talk about closure, interior, exterior, and boundary points of a subset in a topological space. And then we define the notion of continuous mappings. In continuous mapping, as we said, structure preserving maps between topological spaces. And when there is a continuous map from one topological space to another, we say the spaces are if there is a continuous mapping actually that is bijective, it's a continuous inverse. It's called a homeomorphism. And if there is such a homeomorphism between two topological spaces, then the spaces are called homeomorphic. And it is actually one of the fundamental problem in topology in general to identify which spaces are homeomorphic. That is, given two spaces, we want to know whether they are the same or not. And this is a very difficult task. And that is why algebra was employed into the issue. Algebraic tools were introduced to solving this problem of knowing which spaces are the same or not. We mentioned some of the contributions yesterday as part of the scanty history we gave. And then we talk about Hausdorff spaces, when a space is said to be locally Euclidean. And then we define finally n manifold or n-dimensional topological manifold. And a topological manifold is what? It's a second countable Hausdorff locally Euclidean space of dimension n. Then we say the manifold is of dimension n. Then what we did was to look at a few of the examples of that manifold. One of the basic examples we look at is the n ball. Remember, we define n ball, and we also define n sphere. And sphere is seen to be the boundary of a ball. Okay? So we are going to continue that discussion. Today we will start looking at how to construct new spaces out of existing spaces. In fact, this is something we have been doing, but without having to care about what's going on. So today we are going to look at construction of new spaces out of the old ones, or operations on spaces. So constructing new spaces, like topological spaces. If we say spaces in this course, we mean topological spaces from the old spaces. And the first construction is that of subspace. So we define what we mean by a subspace. So if you have a space, you can talk about subspaces. So you can have so many spaces existing within a space, as existing as subspaces. So, and you know, when you are talking about topological space, it has to be accompanied a set, a non-empty set, accompanied with what? A topology. And that is when you call a topological space. So if you have a topological space, and then you identify a subset of the underlying set of the topological space X, then we will define a new topology on Y. This topology will be tau y, or written as tau restricted to y. So it's like you are restricting the existing topology on y by, so did you remember what a topology is? It's a collection of subsets of the space. So this, I want it to be a topology on y. So it should be a collection of subset of y. So it should be collection of subset of y such that this subset is the intersection of y and the open set in x. That is how it is defined. Then this is a topology on y. Tau is a topology. Actually, we have already said it is a topology. So it is a topology on y. But then it can be proved to be a topology. How do you prove that it is a topology? To show that y is there. Yeah. Because y, the y can be written as y intersection x. Yeah. So y is y intersection x because x is containing y. So y is a member of this tau restricted to y. An empty set is actually y intersection empty. So it's there. And if you pick any finite or two members from here, you can also write them as, because if you have u1 coming from the topology here and u2, so u1, u2 coming from tau of y, then by the definition of being here, it means u1 is y intersection v1 and u2 is y intersection v what? v2. But that means u1 intersection u2 is equal to, so it will be y intersection v1 intersection y intersection v2. This is v, sorry. Is that okay? But that will be equal to, so you just perform associativity of this. But then idempotency of the intersection, it means this is v1 intersection v2. But v1 intersection v2 is already a member of tau. So you can write the intersection of any two members from tau restricted to y as the intersection of y with an open set in x. And so therefore this is in tau. So that means this intersection belongs to tau restricted to y. Are you following? So the second requirement for the definition of topology is also satisfied. Okay? And if you take any arbitrary collection of members from here, it should be written as a member, okay? If you take any collection of each of the arbitrary members, that is, if you take a family of members from tau y, then each u alpha is y intersection v alpha. And this v alpha constitutes of now a family of open sets in x. And so the union of this family will still be in x, an open set in x. I hope it's okay. Is that okay? And so if you take the arbitrary union over all the alpha of this family, it will be union over what? Over alpha of this. But then you can write this as, because you have a common factor here, this y, so this is y intersection the union of alpha of b alpha. But this is in tau. And so therefore, the arbitrary union of members from tau by y restricted to y is actually is written as y intersection open sets in tau. So this is indeed a topology. So what I did here is just to verify that it is actually a topology. I hope it's okay. It satisfies all the requirement of it being a topology. So, yeah, okay. So, this topology is what we call the subspace topology, okay, or the relative topology on Y. That is the name. So this is a subspace topology. So whenever we take a subset of a topological space and call it a topological space, emanating from the space, is actually with respect to the subspace topology or the relative topology. I hope it's okay. So like when I was looking at a sphere, you remember we defined a sphere from yesterday in our class yesterday. We defined a sphere and we also defined a ball. But this sphere and the ball, we call them what? We say they are manifolds. So there are manifolds existing in, there are topological spaces existing in the 3D in the three-dimensional Euclidean space. So, but it is a subset of the three-dimensional Euclidean space. So with respect to which topology is it a topological space? It is with respect to the subspace topology. That is the relative topology. Okay? Can I clean here? No? Okay. No, I want to clean this side. All right. Okay, so let me clean here. So the topology tau by y is called the subspace topology, or a second name, relative topology. That is the topology relative to the subspace, the subset. On Y. And the space. So which means we create a new space out of an existing one. Okay, and it's actually a new space. I will show you why it is a new space, because something may happen. That is, a set that was not open originally in the bigger space may now turn out to be an open set in the subspace topology. So we are not saying you just take a subset of the topology, to constitute a topology for the subset. Why? Are you following? But you take the relative topology. You take those subsets of the topology of open set that intersect Y. So the intersection of the open set with Y. That is what you will do. And this is called a subspace of X. So whenever we speak of a subspace, topological space, we are talking about the subset being a topological space with the relative topology. I hope it's okay. In fact, let me give you an example. You can take X. So my first example is to take X to be the set of real numbers. This is a topological space with respect to the standard topology, the topology generated by open intervals on R. Okay? So let me emphasize it with the standard topology. Okay? Call it tau. And take X to be the real line with the standard topology and take y to be the interval minus 1, comma 1. Do you recognize this from yesterday lecture? This is what? The one ball. The ball of dimension 1. Yeah. That is the interval from 0 to 1, close bounded. Okay? So it is, so you see, you can generalize this, my example, to Rn. In Rn, you can always take the n ball, a ball of dimension n. So this is the one ball. What will be the relative topology? It's this one already on the board. What will be the relative topology? Yes. From minus 1 to 1. Yeah, it's the interval. From minus 1 to 1. This interval, all this point here. Minus 1 and 1 inclusive. Yes. Yeah. From 0 to 1. No, it's from minus 1 to 1. Okay. Yeah, well, part of what we discussed yesterday was these topologically they are the same because we imagine spaces are made up of rubber. So even from 0 to 1 is half of this one. But you can stretch it since it is a rubber. Okay, so it's all right. Okay, so they are topologically the same. From 0 to 1 and from minus 1 to 1, topologically the same. Okay, so this will be the all subsets from our definition U of what? Of this interval, such that this subset is equal to the interval intersection V, where V is an open set in R. So it's a union of open intervals. Is that okay? So, and then, so with respect to this topology, this is a topological space. But you know this topological space is not homeomorphic to R because this is compact, but this is not compact. I hope it's okay. So, well, you should note that in this topology, so they are not the same. In the topology, in tau, in the topological space, in the subspace, let me say subspace, Y with tau, the interval minus 0, 1 is an open set, meaning it belongs to tau restricted to Y. Okay? But not open in what? In R. This is not an open set in R with the standard topology. This is because 0, 1 can be written as the intersection of minus 1, 1 with 0, 2. See, this is an open set in tau. Okay? But we know clearly that this thing is not in tau. It's not an open set in R. Are you following? It's not open in R, but it is open in the subspace topology. I hope it's okay. So I'm this example is chosen just to let you know that the idea of source space in topological spaces is not like the way it is in group. You know, in group, if you have a subgroup, whatever is the identity in the group originally must still be the identity here. And the binary operation is the same. And also the inverses of elements in the original group must remain to be inverses of the element in the subgroup. Are you following? But here it's not the same. Open sets may fail to be open set here. And no. Well, every open set is also an open set here. But, well, may fail to be. Things that are closed may turn out to be open here or something like. So it's not necessary that every open set here in the subspace is still an open set in the original space. Like here, this was not open in the bigger space, but it is now open in the subspace. So this you should take note of. All right. And likewise, you can see so many other examples like this, a cycle. I can imagine having a cycle and concentrate only on the cycle as my y. Meanwhile, the entire space R2 is my x. So the entire plane is the space, but I can only see the cycle, point on the cycle to form my subspace. And then the rest, the relative topology will be the intersection of all the open set in the space with this point on the cycle. So you can take the cycle to be a subspace as a subspace of R2. And this is how we will be working most of the time. When I am talking about a cycle, I can see a cycle either in R2, a subspace of R2, or a subspace of R3 in 3 dimensions. Are you following? So you have cycles. So we will be seeing spaces as existing in some ambient space. So you have some space like R3, and a lot of balls are already existing, a lot of spheres, and so many spaces are already existing in R3. There are spaces we are going to talk about, we will see that they do not exist here in R3. They can only exist in higher dimension. Okay? So we don't have that. We can only imagine what they are, but we will not be able to have them like this. Okay? Yeah, but this one, so what is this? This is a cycle. It's actually a sphere, but this is a ball, of dimension 3. And you can also think of seeing the, so what is this one? Of dimension 0. Remember we talked about it? It will be the boundary of this ball. The boundary of the ball of dimension 1. So it will be -1 and 1. And so this can be taken as a topological space, subspace of R. Okay? And you can also see that the sphere S2 is the sphere. You see, you can imagine a sphere like the surface of this thing. So it's existing where? This cannot exist in R2. It can only exist in R3 or higher dimensional Euclidean spaces. Okay? What? Because it's actually the boundary. But as a manifold, we introduced it yesterday, it is a manifold of dimension 2. So you can have 2-dimensional spaces existing in 3D. 3-dimensional spaces. Are you following? So this is a 2-dimensional space existing in 3-dimensional space. So it's a manifold of 3 dimensions. And even a ball can exist here because this is the boundary of the ball. Are you following? Okay. So in general, the sphere of dimension n-1 and the n-dimensional ball, these are subspaces of Rn. Okay, but when you speak of them as spaces, you should understand with the relative topology. Okay? Good then. All right. So this is one way to construct new space out of existing spaces. But then when you have two spaces, you can combine them together, or a number of spaces. It doesn't have to be just two spaces. So many spaces you can have and combine them together to produce a new space, like the product space, product topology. Product space, like product topological spaces. So take spaces x1, x2, xn. So let this be topological spaces with topologies. So respective topologies, tau 1, tau 2, up to tau n. Okay. Then the product topology, the Cartesian products, you can take, because they are sets, so you can take the Cartesian products of this set and make it a topological space by using the existing topologies. Okay? So the Cartesian product, x1 cross x2 up to xn, which I can write as x. So on the Cartesian product, so what I'll do is to define on the Cartesian product, we define a topology called product topology. And this product topology, being a topology on the Cartesian product, will make the Cartesian product of any two spaces to be a topological space. Okay? So we define the Cartesian, the product topology. I will write it as this. This is my Cartesian product. So this is now the topology on X, X being the Cartesian product. By, so this, so what will be open here? Well, so tau of X is the set of all, well, subset of X. So subset of the Cartesian products. Elements here are n tuples, okay, such that for all P in U, an element of U, there exists an open set V, Vi, so Bi in tau I. Well, if you take a point here, it is x, it will be x1, x2 up to xn, because this is a Cartesian product. So if you take a subset, the points are n tuples, like I said. So for every point from this subset, there exists an open set, this open set up to I of them, okay, such that xi is an element in vi for each v. So vi here is running from 1 to n, okay? And the product v1, the Cartesian product v1, v2 up to vi, vn is inside u. So this is, okay? That's how we define the topology, okay? The product topology. Okay? Is that what? Between Vn, yeah. So, well, it's like you are saying, corresponding to every point, this point are tuples. So they are a neighborhood of the coordinate of that point, such that the Cartesian product of the neighborhood will be sitting inside this U. Okay? Maybe let me just show you. Imagine maybe this space x1 is 2 and x2. So you can think of real numbers, huh? So a set will be open, this is a set like this, can be anyone. This is my U. It will be open if and only if for every point in here. So a point here, P, is having coordinate x1, x2. So for every point inside, there is, it has this coordinate. There is a neighborhood V2 and a neighborhood V1. Well, sorry. This should be x1, V1, and V2, okay? So there is a neighborhood of the coordinates in here. The neighborhood will be in the topology of this space x1, and this is my x2, okay? So there is a neighborhood of the coordinate x1 in the topology of x, so an open set in the space x1. That is what I mean by this. And an open set in the space x2, so that the Cartesian product of v1 and v2 will be sitting completely inside you. So that if you take the Cartesian product of this neighborhood, so suppose it's here. This is the Cartesian product of the neighborhood. It should lie entirely in you. Okay, then U is open. So if you imagine like it is not open, U, like you have a point here, so no matter how hard you try to get a neighborhood of this point or a neighborhood here, at the end of the day, the Cartesian product of the neighborhood at the y-axis and the one at the x-axis will contain point. It will not sit completely inside you. Are you following? So this is when you now say this space. This is how you identify members of the topology in the Cartesian product or in the product space topology. Yeah, so that is it. Well, I have given you already one example. Because this is x1 cross s2, and that is r2. So that is how the topology of the R2, the standard topology, is constructed from the topology in R1. Are you following? Because it's R1 cross R1 that give rise to the plane the real plane. That is the okay. So, and generally, Rn will be R cross R cross R times, N times, not R times, sorry. Okay. Let me give you some more examples of this product topology. So example 1, if I take my space, this space X, so you take I to be the interval 0, 1, okay, and this will be the, and see it as a topological space sitting inside the real space with respect to the subspace topology, okay. Then we can take M tuples product of this space to construct a new space. Then the space I M, which is I cross I, because I have a topological space, then I can multiply it, the Cartesian product of it by itself, up to M times to be a new topological space. This is a product space, okay? In fact, I haven't mentioned over there. That is that space X with respect to the product topology, not like this. It's called the product space. Product topological space with respect to the product topology. So you can obtain the product space M times product of this, because this is seen as a topological space. In fact, it is a ball, okay? It's a ball. It doesn't matter actually, because I have told you it's isomorphic, it's homeomorphic, sorry. It's homeomorphic to what? To the one ball. Remember, one ball is minus 1, 1. But these things are homeomorphic. Okay?
But it's not homeomorphic to R.
It's not? No, but none of them is homeomorphic to R because of what I mentioned. Okay? All right. So this will still be homeomorphic to M ball, if you understand what I'm saying. Because this one is already homeomorphic to one ball. So you can take a ball and take the product of ball n times and get an M ball. Are you following? But you know this, when you visualize this is no longer seen as a ball. It's a kind of rounded shape. When you do I cross I, it will look like what? A square. I hope it's okay. In fact, if you can see that I1 is what? Is I1 is just this one, 0, 1. But what is I2? And this is homeomorphic to the ball of minus 1 and 1. Homeomorphic to it. But how about I2? I2 will look like this, because you are taking I and crossing with itself, and it's everything inside. That is homeomorphic to a disk. Remember, a disk is our B2. It's homeomorphic to a disk. So this is another way you look at a ball, as a rectangle. This space is called M cube. The space, this one, it has a name. It is called M cube. It's a cube. you know. So a cube of dimension 1. Okay? Okay, if you take dimension 3, there's a manifold of dimension 2 here. But for dimension 3, you get what we know to be a cube. That is a cube of dimension 3. So I3, and this one now is existing in, because this space is a subset of Rm. It's a subspace of Rm. So R cube is existing in R3, I cube. And it will look like this. So it's a cube. But a cube, solid, not hollow. What do we call a hollow cube? Well, for a ball, hollow, the inside is only the boundary of a ball is called what? Sphere. But if it is a cube, the boundary is called what? This one is 3 cube, that is, but the common name is just cube.
Yes.
But this we say is isomorphic to what? To a ball. A ball. Yeah, a solid sphere. A ball. So this is 3 ball. But the surface, the boundary of this ball is what we call sphere of dimension 2. You remember? But how about the boundary of this one? Meaning inside is hollow, only the boundary, the surface, is what? It's called a box. It's a box now. So a box is isomorphic to, a homeomorphic to a ball. I hope it's okay. So the boundary of a cube is called a box. This is an M box. M box. But it is isomorphic to Sm minus 1. And an M box is actually of dimension m minus 1. Because the sphere is of dimension m minus 1. I hope it's okay. Yeah. So don't get confused. And you remember the sphere is a boundary of what? The ball of dimension m. Okay? So topologically, there is no difference between box, sphere, cube, and ball. I hope it's okay. So please get this thing clear. But, well, then, how about this? We cannot draw this one because this one now is in R4. It's in it's in 4 dimension. Okay? Yeah. It is called tesseract. Tesseract, I think. All right. So, that is my first example. M cube. M cube is a product space. It's a manifold, but it's constructed out of the existing manifold from one ball or one cube. Just an interval, 0 to 1, half interval. My second example will be to take a cycle. So take X to be the cycle. Yeah? Sitting in what? It can be in R. A cycle is a subspace of R. You can see it as a subspace of R. It can be in R2. It can be anywhere. But if you take a cycle and multiply it m times, you get what? Yeah. And the space, which space? This one. Uh, S1 cross S1. So the product space, this is donated by TM, and it is called, so you see we can construct always new spaces from the existing one like this. So I can take a space and get something entirely not homeomorphic to the cycle, because this cycle is of dimension 1. Now by the time you multiply with itself, you get a space of dimension 2. Okay, I'll give you a formula to calculate the dimension of a product space. So this product space is called, it's a product space. It's called what? An M torus. M torus. A torus of dimension M. Okay? So I can draw torus up to dimension 2, but from dimension 3 upward, I don't know how to draw. Okay? So let us, so T1 will be what? The cycle. So it's just a cycle. That is T1. So a torus of dimension 1 is just a cycle. No problem. And then a torus of dimension 2 would be S1 cross S1. So, and how is this one looking like? It's like you are multiplying a cycle by itself. You take a cycle, it's like you are taking a cycle in 3D and rotating it. Imagine you have the cycle like this. So if this is a cycle and you rotate it, it's like you have two cycles. You have a cycle like this, and you have another cycle like this. And then you rotate this cycle around the other one. It will sweep a point space. So imagine it like, so let me just draw what it is. So it is this one. That is it. You can, so that's a torus. Surface of this thing, I mean surface of this thing. The surface. It's not a solid like tube, like tube or donuts. But donut, I mean hollow. Okay, so sometimes it's called donut because dimension 2. So imagine there was a cycle like this, and then a cycle like this. And you rotate this cycle around the other one. So it sweep some point. And so you have donuts. So this is a torus of dimension 2. Okay? Well, of dimension 3, I cannot draw. This is as far as I can go. It's called, so this is a cycle, and this one is called donut. No, two torus. Two torus. We are going to look at other ways of constructing this space. So you use cycle to construct a cycle is of dimension 1, and then you now construct a space of dimension 2. So I said dimension 2, from a space of dimension 1, you have dimension 2. And then you can have higher dimensional torus, like m dimensional torus, when you multiply a cycle m times. But then the formula to get the boundary, if you have this space, x1 cross x2 cross xn. The boundary of the product space, it can be obtained as the union from I equal to 1 to n of the boundary of, well, x1 is also a product space. So it's x1 cross x2 up to, xi minus 1, well, it's all right, I don't know. So up to the boundary of xi cross xi plus 1, and then the boundary of xn. I don't know that you understand what this is. Every time you arrive at I, you take the boundary in the Cartesian product. I think, let me just write it in. So, like with M, like if you have X cross Y, so it will be X, the boundary of Y, union Y, the boundary of X, the boundary of X cross what? Y. Do you remember this thing? Do you remember this? Like product rule of differentiation, or Leibniz rule. Leibniz rule. So that's what the boundary operator is doing. Taking boundary. In fact, that is exactly what it is. It's a product rule. Keep this one constant, differentiate that one, plus union, differentiate this, keep the other factor constant. So you have known this already. So it's like when you are looking for the boundary of what will be the boundary of this? What will be the boundary?
X1,
Yeah.
they were X2, union. The boundary of it is X1, but rather the boundary cross the boundary of X2.
Yeah, so it will be, so it's like you can imagine as if you are having, so this is I, and this is what? I again, because this is I cross I. Okay? So it's going to be the I cross boundary of what? I. But what is I? I is this. I know, and you are crossing with the boundary of I, and the boundary of this I is just 2 points like this. Okay, let me show you in the picture. So it will be union boundary of I cross I cross I. So look at it. Look at this one. We know what this boundary is clearly. It is actually this one. Is that not it? Okay. So imagine you have this. So this is your interval I, and you have the interval I over here. It's from 0 to 1. I should have drawn it like this. It's from 0 to 1. So this is my I, and this is my second I. This is my I also. So it is this I'm talking about. So this is the boundary. So but if you look at here, when you say I, it is this. Okay? And then the boundary of I in the horizontal axis will be 0 and 1. Okay? But if you cross this, what do you get? You get this line. That is the set of all ordered pairs whose second entry is 0 and second entry is 1, while the first entry is from this I. So, and then this will be this first factor. Union, what? this I, the boundary of the first I here in the horizontal axis, which are these 2 points, and then with this I, you take the cross product with this I. And then what will be the cross product? It will be this line here and this line over here. So you take this union, you get the boundaries. Are you following? So you can see it clearly here. But now what is the boundary of the torus? What will be the boundary of the torus? Well, a torus is S1 cross S1. So it will be S1 cross boundary of S1 union boundary of S1 cross S1. But do you have anything in the boundary of S1? The circle is it having boundary? Does it have boundary? The circle boundary is empty. So S1 cross empty set will still give you empties. So everything is empty there. Are you following? So actually the boundary of torus is an empty set. It doesn't have boundary. Just like cycle doesn't have boundary. I hope it's okay. Is that okay? Okay. But how about dimension? If you take spaces, if I take m spaces, the dimension of x1, x2, xm will always be equal to m, because the dimension of this space plus it will not equal to m. It is the dimension of the sum of the dimensions. So to be from I equal to 1 to m of the dimension of xi. So if you take the product of a space of dimension m and a space of dimension n, the resulting space will be of dimension m plus n. Is that okay? All right. So a torus has no boundary. It has no boundary. You know, boundary of a space is like here, like this paper. This is the boundary. The boundary is just a cycle. This square here. I hope it's okay. Cycle. That's the boundary. The boundary of a space is those points from which you exist, the space. Because if you imagine there is an ant moving on this space, on the surface of this paper, if it reaches here, it will fall down. I hope it's okay. But if it were a torus, you know, a torus, this you can make a torus by a piece of paper like this. You, well, I'll talk about identification spaces. So if there is an ant moving on the surface of this torus, there will be no any time when it will fall off of this surface. So it will keep on moving continuously because there is no boundary. It can never go out of the space. So it has no boundary. No boundary. All right. So, and that's when we say a space is closed. Sometimes we can talk about closure of space. If you say space is closed, it means no boundary. So it's a closed space. Not closure in the sense of the complement of the set is open. No, no. The space in its entirety being closed, it means it has no boundary. I hope it's okay. So this is it. You can claim. Okay. So there is again another new space we can construct out of the existing one. My example 3. This should be the fourth example or third example. The third example. Okay. All right. So, like you can take a cycle and take the product with the interval 0, 1. So if I take a cycle a cycle and take the product with interval 0, 1, the resulting space will be a cylinder, finite cylinder. So this will be cylinder, but finite cylinder. If you do S with R, you get an infinite cylinder. Okay? So, and this space look like this. This is a cycle. But the surface of only the surface, not everything. Yeah. A cylinder like this. Okay? Okay. I think we can stop here so that in the next class we look at another operation on spaces where we can form new space from existing one, taking quotient of spaces. Thank you very much.